All right, so here we're going to cover a cool little fact. This is a thing about the determinants and areas, which you probably like could have had some guesses about in the cross product section. There's a thing in the cross product section where I say the magnitude of the cross product is the magnitude of the two vectors multiplied times the sine of the angle between them, right? It's the area of the parallelogram. That feels a little bit circular if you took Calc 3. I told you that I'd explain why that was true here. So this is me taking the opportunity to kind of explain why. So I'm going to do this in a 2 by 2 case because it's a little easier to see. It's much easier for me to draw pictures. The 3 by 3 case works the same way. It's just a little bit harder to see. So here's my kind of claim, right? My thing I'm going to look at. I'm going to say my claim is that the absolute value of the determinant of A is equal to the area of a little parallelogram here. And you can make this parallelogram with either the rows or the columns of A, right? So here we're going to have, and I'm going to go for a row, right? So this is going to be row 1 of A. So I'm just going to call this R1 and R2 here, right? So those are my two row vectors. You could just as easily do this with the column vectors. If you want to do this with the column vectors, you just apply the exact same argument to A transpose. And we know that the determinant of A and A transpose are the same. So you can do this with the columns as well. It's totally fine. Works exactly the same way. So in order to prove this, I'm going to need to go back to something. My properties of the determinant. So these are the primary properties of the determinant. These three are enough to uniquely define the determinant. So I'm going to pull a little trick. I'm actually not going to show that when I calculate the determinant of a matrix A, that I just go ahead and get this area. That's actually going to be a little bit hard for me to do. So what I'm going to do is make this other claim. I'm going to say these three properties make the determinant, and then I'm going to show that these three properties are basically satisfied for this area. And then because it's unique, it must be the same thing. So what that means is I just need to essentially check these three things, right? So one is the determinant of the identity matrix 1, right? So is the absolute value of the determinant of A equal to the area of the square, right? The reason it's a square is when I'm taking these two rows out of the identity matrix, right? So I'm looking at the determinant absolute value of I. Well, I know this is 1. And I'm wondering, is this the same as the area of this little square? So this is, oh, I said these were row 1 and row 2. I'm just going to say this is 1, 0, and this is 0, 1, right? This is actually just the unit box, right? And that actually does indeed have an area of 1. All right, so thing 2, the determinant flips signs with row exchanges. Well, because I've got the absolute value on this, it doesn't really matter. I can just invent a concept of signed area, right? So here where I put row 1 and row 2, that actually probably has the opposite area. So I'm going to make this row 1 down here and this row 2 up here. Because my claim is about the absolute value, it doesn't matter. But if I just come up with a concept of like signed area where like, oh, okay, if the right hand rule is satisfied, I count that area as positive. If it's left hand ruley, I'm going to count that area as negative. That'd be totally fine. We could do that. So I'm just going to kind of put a check mark by that because I talked my way through it. All right, for thing 3, I've got this linearity in each row. This is a little funky, but let me draw a couple of pictures. So here's one of my pictures. I've got a row 1 and a row 2, right? And I'm thinking about the area of this, right? So if I were to multiply one of the rows by a scalar, right? So that'd be me saying, all right, I'm going to scale up row 1 to something like this. And then I'm looking at the area of this parallelogram. Well, if I scale up row 1, I'm also going to scale up this vector here, right? And then I'm going to end up with this vector here? Well, actually, as it turns out, if I multiplied R1 by a scalar, that just made this thing longer. That actually just scaled up the area by a factor of t as well, or whatever I scaled, right? So if the blue was TR1, then in black, I had an area of, say, A. And here, I have an area of TA, where T is the scalar that I scaled up R1 by. That actually checks out. That's kind of cool. For the other argument, you're like, okay, so what does it mean to be linear in? That means I'm adding two rows together, and then that should be the determinant of, okay, so the area, if I add two vectors. So I'm going to say this is my row 2, right? And then I'm going to put row 1 kind of regular there. And then I'm going to say, all right, I've also got like row 1 prime. So the way I'm going to do that is I'm going to go like this off the end. This is going to be like the new row 1, right? That's going to be this Ri prime here. And then I'm going to draw my little parallelogram. So I've got this parallelogram here, right? That's the kind of A parallelogram, right? And then here I've got another parallelogram off the end. I'm going to call this the A prime parallelogram, right? So that's kind of the right-hand side. And I want to say, all right, look, where's R1 plus R1 prime? Well, that's a vector that goes like this, yeah? So that blue vector in there is R1 plus R1 prime. And well, in order to make that parallelogram, I've got the R2 vector just sticks straight up. I've got an R2 vector sticking straight up over there as well. And then here I've got this is R1 plus R1 prime again. Notice this kind of cool fact. This area up here is the same as this area down here. So the area of that blue parallelogram in the back there is actually the area of these two parallelograms added together. That's enough for me to say that the determinant actually is the same as the area of the parallelogram, at least up to absolute value. Again, develop a concept of signed area. This is all chill, right? This is a very cool little fact. This actually pretty much immediately gets me the kind of next thing I'm going to work at. So the next thing I'm going to work at is the volume of a box. So check that out in the next video. You'll see this thing called the scalar triple product, which is real cool. We use it some in Calc 3. Plus, it's just neat.